This is MSJ Chem. In this video, I'll be looking at high-resolution H1 NMR. We'll start with a comparison of low-resolution and high-resolution H1 NMR spectra. On the left, we have a low-resolution spectrum. On the right, we have a high-resolution spectrum. In a high-resolution spectrum, what looked like single peaks in the low-resolution spectrum are split into clusters of peaks. For example, this peak here in the low-resolution spectrum is split into 4 peaks in the high-resolution spectrum. And this peak in the low-resolution spectrum is split into 2 peaks in the high-resolution spectrum. The number of peaks tells us about the number of protons attached to the adjacent carbon atom. In this table, we have the number of adjacent protons, the number of peaks, the type of splitting, and the relative intensities of the peaks. For 0 adjacent protons, we have 1 peak and the type of splitting is a singlet. For 1 adjacent proton, we have 2 peaks and the type of splitting is a doublet. For 2 adjacent protons, we have 3 peaks and the type of splitting is a triplet. And for 3 adjacent protons, we have 4 peaks and the type of splitting is a quartet. So from this table, we can see that if there are n number of protons attached to the adjacent carbon atom, we will have n plus 1 number of peaks. For example, if there are 2 protons attached to the adjacent carbon atom, then we have 2 plus 1 equals 3 number of peaks. In the final column, we have the relative intensities of the peaks, which can be deduced using Pascal's triangle. Next, we'll have a look at the type of splitting patterns in more detail. For this CH3 group, the adjacent carbon is attached to 0 protons. Using the n plus 1 rule, we get a single peak, which is known as a singlet. Next, we look at a doublet. For this CH3 group, the adjacent carbon is attached to 1 proton. Using the n plus 1 rule, we get 2 peaks, which is known as a doublet. Next, we have a triplet. For this CH3 group, the adjacent carbon is attached to 2 protons. Once again, using the n plus 1 rule, we get 3 peaks, which is known as a triplet. And finally, we look at a quartet. For this CH2 group, the adjacent carbon is attached to 3 protons. Using the n plus 1 rule, we get 4 peaks, which is known as a quartet. And here we can see the relative intensities of the peaks, which can be deduced using Pascal's triangle. Next, we look at an example. Here we have the high-resolution H1 NMR spectrum for ethyl ethanoate. In this spectrum, we can see that there are 3 main clusters of peaks, which means there are 3 different chemical environments in which protons are located. Next, we'll use the values of the chemical shifts to identify the type of protons in each chemical environment. Starting at the right, the value for the chemical shift corresponds to the 3 protons in a CH3 group. The next peak has a chemical shift of 2.0 ppm. This chemical shift corresponds to the 3 protons in a CH3 group that's bonded to an ester group. The next cluster of peaks has a chemical shift of approximately 4.0 ppm. This chemical shift corresponds to the 2 protons in a CH2 group that's bonded to an ester group. Next, we look at the splitting patterns for each cluster of peaks. We'll start by looking at the cluster of peaks on the right. As you can see, there are 3 peaks, which is a triplet. If we look at the adjacent carbon atom, which is highlighted in red, we can see it's attached to 2 protons. Using the n plus 1 rule, this produces 3 peaks, which is a triplet. Next, we only have 1 peak, which is a singlet. If we look at the adjacent carbon atom, we can see it's attached to 0 protons. Using the n plus 1 rule, we get 1 peak, which is a singlet. And finally, we look at the cluster of peaks on the left. As you can see, there are 4 peaks, which is a quartet. If we look at the adjacent carbon atom, we can see it's attached to 3 protons. Using the n plus 1 rule, this produces 4 peaks, which is a quartet. And here we have the relative intensities of the peaks. For a quartet, it's 1 to 3 to 3 to 1. For a singlet, it's 1, and for a triplet, it's 1 to 2 to 1. Next, we look at the integrated trace. The area under each peak is proportional to the number of protons in that chemical environment. The heights of the integrated trace can be used to obtain the ratio of the number of protons in each environment. So from this integrated trace, we can see that the ratio of the number of protons in each environment is 2 to 3 to 3.